Earlier in this unit, we described the spring force, that is described by Hooke's law, the force exerted on a mass due to a spring. We also started to describe the energy transfer associated with a mass attached to a spring as it oscillates. In the course of doing so, I began to hint at the existence of what is called spring potential energy. Let me now formally describe exactly what is meant by spring potential energy. The steps that you're about to see, both qualitatively and mathematically, are identical for what we've already seen with respect to the force of gravity in describing gravitational potential energy. Recall how I began my description of the force of gravity and gravitational potential energy. You take an object, for example, and you lift it vertically through some displacement. The work done by gravity is negative mgh. Therefore, the work done against the force of gravity, positive mgh, that then becomes the potential energy of the object. And then if I release the object, that potential energy is transformed into kinetic energy as the object falls. We also saw mathematically that gravity is an example of a conservative force. That is, the work done by that force over a closed path is equal to zero. This then, in the context of the pendulum, literally proves the existence of potential energy, and that then eventually led to our statement of conservation of energy. Same thing now with the spring force in the following sense. Let's say that I take an idealized spring and I displace it like so from the equilibrium position. As we'll see, the work done by the spring force in such a situation is negative 1/2 kx squared. Therefore, the work that I do against the spring force is positive 1/2 kx squared, and that then becomes the spring potential energy of the object. I then release the object like so, and that spring potential energy is transformed into kinetic energy as the object, for example, passes through the equilibrium position. What we will find is that, like gravity, the spring force is conservative. That is, we'll calculate the work done by the spring force over a closed path and we'll show that it's equal to zero. In doing so, we'll prove the existence of spring potential energy, and that will then lead us to another statement of conservation of energy. Okay, now to conceptualize all of this, what we're going to do is have a horizontal situation of a mass attached to a spring. It will then oscillate about the equilibrium position, and it will do so on a horizontal frictionless surface. This is analogous to the pendulum situation that we use to describe gravitational potential energy and ultimately conservation of energy. So let's begin to lay out the situation in the following way. All right, so what we're going to do is we're going to calculate the work done by the spring force over a closed path. And then, as I just mentioned, here's how we'll conceptualize it. Okay, what I'm going to do is take the mass and attach it to a spring like so horizontally. And then right here is the equilibrium position. We're going to say that this right here is position A. And then I'll either stretch out the spring or compress it. Remember, it doesn't matter, for position B. So let's say it right here, for example, is the stretched out spring. We displace the spring like so, a distance x from the equilibrium position. The spring force itself is back towards the equilibrium position, and then we'll refer to this as position B. Okay, now recall from earlier in this unit how you calculate the work done by the spring force. We have to set up the following integral. The work done by the spring force is equal to the integral of minus kx dx. Recall this line integral that we used in situations earlier when calculating the work done by the spring force. All that will change as we go from A to B and then backwards from B to A are the limits of integration. They'll basically just reverse. So let's see what happens first of all as we go from A to B. Okay, so as we go from A to B then, the lower limit of integration is going to be the value of x at the equilibrium position, which is 0. And the upper limit of integration is going to be the value of x here at position B. And then when you integrate minus kx dx, you always end up with the exact same antiderivative. That is, negative 1/2 kx squared. And then we have to plug in our limits of integration. First of all, we have to plug in the x into the expression, and when we do, we just get negative 1/2 kx squared, and then minus with the 0 plugged into the expression, and it just ends up being minus 0. So then therefore the work done by the spring force when stretching it out, for example, from point A to point B on the diagram is negative 1/2 kx squared. Okay, now let's go backwards. Let's go from B to A. So So when we go from B to A, it's the exact same work calculation, but now we just switch the limits of integration. So the work done by the spring force is still going to equal now integral of negative kx dx, but now we go from position x to position 0. When you switch the limits of integration, instead of getting a negative 1/2 kx squared, you end up with a positive 1/2 kx squared. Like so. So then add the two terms together to get the work done by the spring force over the closed path, and no surprise, it's equal to 0. Okay, so add together, and the work done by the spring force over the closed path is 0. Okay, now here's what that means. As the object oscillates, the spring force is not adding energy to nor removing energy from the object. However, as the object oscillates, it changes in value of kinetic energy. Therefore, that kinetic energy has to be transforming back and forth into something else. It has to obviously be transforming back and forth into spring potential energy. So like gravity, the spring force is also conservative. Potential energy exists. Once again, just think of it merely in the following way. The work done by the spring force over the closed path being equal to 0 means that the spring force doesn't add energy to or remove energy from the object. Instead, what it does is it transforms the kinetic energy back and forth into spring potential energy. So we've once again proved that potential energy exists here. It's now just in terms of the spring force as opposed to gravity. Okay, how do we quantify spring potential energy? Well, we basically just take 1/2 of the calculation that we just performed. Okay, let me go ahead and do some erasing here. Okay, let me rewrite this like so, as we go from A to B. Okay, and now up here, let's change the heading. Here's how we quantify spring potential energy. Okay, so when stretching out a spring from position A to B, the work done by the spring force, as we just calculated, is negative 1/2 kx squared. Okay, now, therefore, the work done against the spring force when stretching out the spring, this is the minimum energy necessary to stretch out the spring, in other words, overcome the spring force. By definition, is the opposite of the work done by the spring force. So showing all of the negative signs, it's the negative of negative 1/2 kx squared. This is equal to positive 1/2 kx squared. This is analogous to the following. When lifting an object vertically, the work done by gravity is negative mgh. Therefore, the work you do against gravity is positive mgh. Same thing here. In this case, the work done by the spring force is negative 1/2 kx squared. So then therefore, the work that you do against the spring force is positive 1/2 kx squared. We then interpret this quantity, positive 1/2 kx squared, to be equal to the change in spring potential energy as we go from position A to position B. Spring potential energy is labeled as capital U sub S. Okay, now, technically speaking, it's a final value at position B minus an initial value at position A. However, position A, keep in mind, is our equilibrium position. So then therefore, if you're not stretching or compressing the spring, obviously the spring potential energy is then therefore equal to 0. So this term right here, the initial spring potential energy, that right there is 0 at equilibrium. Therefore, the final spring potential energy at position B is 1/2 kx squared. Exact same series of steps here as I did with gravitational potential energy. Now instead it's in terms of the spring force. The only difference is that instead of seeing all of the mgh's all over the place, in this case you're just seeing 1/2 kx squareds. Okay, here's then how we arrive at a statement of conservation of energy. So what we do is we apply the work energy theorem between any 2 points in the oscillation. Apply net work equals change in kinetic energy between any 2 points in the oscillation. Okay, I'm running out of room here on the lower board, so let me go ahead and do some erasing. Okay, now when you apply the work energy theorem to the horizontal oscillator, that is on a horizontal frictionless surface, the only thing that matters is the work done by the spring force. That will then be the left-hand side of the expression. So the work done by the spring force equals change in kinetic energy. But from the top board still, the work done by the spring force is the opposite of the work against the spring force. And also still on the top board, the work against the spring force is the change in spring potential energy. Like so. And then just as I did to arrive at a statement of conservation of energy for gravity, now what we do as a last step is we move this term to the other side, and that then gives us the following. Like so. And there is once again our conservation of energy expression. The left-hand side of the expression is once again still interpreted as the change in the total energy E of the object. So between any 2 points in the oscillation, if you add together the change in kinetic energy plus the change in spring potential energy, you end up with 0. The change in the total energy E is equal to 0, therefore the energy is conserved. An identical way of saying the same thing, but in this case for a single point in the oscillation, is as follows. At a single point in the oscillation, the total energy E, which is a combination of kinetic and spring potential energy, is equal to a constant. This is another way of saying that the energy is conserved, but in this case, just for a single point in the oscillation. And now let's immediately look at a basic example involving a horizontal oscillator, and we'll use conservation of energy to analyze it. The great thing about using the expression is that we no longer have to do any dot products and we no longer have to do any integrals when calculating, for example, the work done by the spring force, because we already know what the punchline is, that is spring potential energy, 1/2 kx squared, and we already know that the energy is conserved. So let me go ahead and do some erasing here, like so. And now let's immediately access our example. Okay, I have it here on my screen. Let me read it to you. Make sure, of course, as always, that you copy it into your notes. Okay, a fixed horizontal idealized spring is attached to a mass of 1 kilogram on a horizontal frictionless surface. The spring constant equals 10 newtons per meter. The mass initially stretches the spring a distance of 0.5 meters from the equilibrium position. We'll find the speed of the mass as it passes through the equilibrium position, and then we'll find the distance on the other side of the equilibrium position that the mass compresses the spring, thereby now describing an oscillation using conservation of energy. Okay, so let me go ahead and take a look at part A of the problem first. We'll set it up in the following way. Okay, so right here is our mass attached to the spring. Right here is the displacement x equal to 1/2 meter, and then we have the following values. The mass of the object itself is 1 kilogram. The spring constant k is given to us as 10 newtons per meter, and then we release the object from rest. Okay, and then we're asked to calculate the speed of the object as it passes through equilibrium. So here's the equilibrium position like so, and the object has a speed v as it passes through. And now we set up our conservation of energy expression. 0 equals delta k plus delta u sub s, and now we just start filling in all of our terms. So first of all, the change in kinetic energy. We will have a final kinetic energy here with the speed v, so that's 1/2 mv squared, minus then the initial kinetic energy of 0 because the object begins at rest. And now we have the new term, the change in spring potential energy. All that we have to fill in is final minus initial, the value of 1/2 kx squared. So first of all, the final spring potential energy. The final spring potential energy is 0 because the object is at the equilibrium position at the end of part A, and then minus the initial spring potential energy here when we begin by stretching out the spring to displacement x. So then therefore I have final minus initial spring potential energy looks like this. And now we just solve for the speed v. So to do so, let's take this term here and move it to the other side. Like so. And now in this case, this right here is the energy transformation that occurs, and there's no question marks associated with spring potential energy at this point. So in this particular case, all the spring potential energy that we start with here transforms into the same amount of kinetic energy as we pass through the equilibrium position. And now we just solve for the speed v. Notice once again, however, that the mass m nor the spring constant k, neither of those two terms cancel. So the speed of the object in part depends upon those values. Okay, let's go ahead and finish the math here for part A. I'm going to cancel out the 1/2 from either side like so, and then divide the m to the denominator here on the left-hand side, and then take the square root now to get the speed v by itself. So after you do these couple of minor mathematical steps, you end up with this expression here for the speed v. Okay, let's go ahead and plug in. So let's see, I have the square root of 10 divided by 1, so square root of 10. There we go, and then multiply by the displacement of 1/2 meter, and this comes out to be 1.58 meters per second. And then in part B of the problem, then let's just calculate quickly how far it compresses the spring on the other side of equilibrium. Obviously, it's going to be 1/2 meter again, but ultimately, here's how you show that. Okay, so now let's set up part B in the following way. Okay, right here now at the equilibrium position is my object with an initial speed here of 1.58 meters per second. So I'm taking the speed that we calculated earlier in part A and applying it here. Okay, and then we compress the spring like so, coming to rest for an instant, and then right here is the unknown displacement x. And now we once again just set up our conservation of energy expression. When we do, the terms are basically just backwards of what you saw a few moments ago. Okay, so here's conservation of energy, like so, and now we just start filling in our terms. First of all, change in kinetic energy. We're going to have right here a final kinetic energy of 0 because the object ends up at rest, and then minus the initial kinetic energy with the speed v0 as it passes through the equilibrium position. And then we have change in spring potential energy. We will have a final spring potential energy here of 1/2 kx squared, and then minus the initial value, which is equal to 0, because we begin part B of the problem at the equilibrium position. Like so. And now we just solve for x. So to do so, let's move this term here to the other side. I'll toss away my zeros as I do. Like so. And I get to this expression here. And this expression here is the same thing as it is in part A of the problem for the energy transformation. It's just backwards. In this case, all the kinetic energy that we have here at the equilibrium position transforms into the same amount of potential energy as we compress the spring. Because this equation here, however, is mathematically identical to this expression here, if we went through the motions to solve for x, we would once again just get 1/2 meter. Like so. So this simple harmonic oscillator will now execute simple harmonic motion in this manner forever because the energy is conserved. Every time that it passes through the equilibrium position, it will do so at a speed of 1.58 meters per second, and will alternatively stretch and compress the spring 1/2 meter with every oscillation. Okay?